In our last class of kinetic theory chapter, we already discussed about the perfect gas equation. Okay. Uh, Today we will discuss the more useful forms of a perfect gas equation. So first of all, I need to write down the topic. That is, so using the perfect gas equation we have is PV is equal to mu RT, where mu is the number of moles, number of moles, and R is equal to Na, that is universal constant, and the T is absolute temperature. Now, value of R at absolute temperature T is 8.314 Joule mole inverse Kelvin inverse. Here mu is equal to, where m is the mass of gas containing n molecules, m naught is the molar mass, and n is the Avogadro's number. Now, another useful form of equation 1 is, let us suppose this is our equation 1, that is P is equal to rho RT upon m naught, where rho is the mass density of the gas. Density of the gas. Now, a gas that satisfies this equation, which is equation 2, exactly at all pressures and temperature is defined as an ideal gas. So, we can write as a definition of ideal gas, a gas which satisfies equation 2 exactly at all pressures and temperature is defined as ideal gas. Now, an ideal gas is just a simple theoretical model of a gas. Actually, no real gas is truly ideal. Okay? At low pressures or high temperatures, the molecules are far apart and molecular interactions are negligible. Without interactions, the gas behaves like an ideal one. So we can write here, at low pressures and high temperature, the molecules are far apart, the molecules are far apart, and molecular interactions are negligible. And molecular interactions are negligible. Without interactions, the gas behaves like an ideal one. Behaves like an ideal one. If you fix mu and T in equation 1, what we get? We get PV is equal to constant. Okay. So keeping the temperature constant, pressure of a given mass of gas varies inversely with volume. Okay. So, and this will be the Boyle's law. So we can write Boyle's law here. Boyle's law. Keeping temperature constant. Pressure of a given mass. Pressure of a given mass of gas varies inversely with volume. Okay. Now there is one more gap we have here. Okay. Now, if finally consider a mixture of a non-interacting ideal gases, mu1 moles of gas 1, mu2 moles of gas 2, etc. in a vessel of a volume, what we have? We need to draw a graph. between pressure and volume. Here let us suppose it's 20, then 60, then 100, then 140, 160, and that is 220. It's zero point 0.2, it's zero point 0.4, it's 0.6, and here it is 1.6. Now draw a graph according to this. What we have, we now there is a horizontal curve, that is, so these are the temperature distance. So here we can clearly see that is T1 is greater than T2 is greater than T3. If this is T1 and this is T2 and this is T3, and this is the actual T1, this is the actual T2, and this is the actual T3. Now this is the figure, or this is the experimental PV curve, basically experimental PV curve, solid lines for steam at 3 temperatures compared with boils, that is dotted lines of 2289 and V in units of 0.0 liters. Next we will discuss in next lecture what will be the considerations of mixtures of non-interacting ideal gases. Okay, some more forms of ideal gas equations and their relations between pressure and temperatures. Next class we will discuss the TV curves, which are experimental again. So here all these are for today. Thank you.